as I told you yesterday, the quiz will cover the improper integrals, what we did yesterday, the comparison test, and the partial fractions decomposition. Okay. All right, I'm gonna give you 5 minutes to solve this question. Okay, about yours, I don't know exactly because I'm still marking, but I guess by next week I'll be done. I'll send you, the your third test. Okay. Welcome, Mom. So you guys are done? All right, 2 more minutes. Just to give you a hint, so you guys need to use the partial decomposition in order to get the integral. Okay, I'm gonna give you 2 more minutes. Use partial fractions decomposition because it's gonna be part of your upcoming quiz scheduled next week. All right, so let's solve this this question. All right, so we have an improper integral of type 1 because of infinity, and as we've seen, we're gonna remove infinity and substitute by t, and we'll let t going to infinity. So this integral is equal to the limit when t goes to positive infinity of integral from 1 to t of 2 over x squared plus 2x dx. And this is the first step. So next we have to evaluate, this integral in terms of t. And when we get it, so we come back here, return here, and just substitute the integral by its value and calculate the limit when t is going to infinity. So second step, we just want to calculate this integral. So 2 over x squared plus 2x dx. Okay, and as I told you guys, have here a rational function, and I told you, a couple of weeks ago, when you have a rational function to integrate, the best method gonna be degree 1, 0, and denominator is a polynomial function of degree 2. So it means the two conditions are satisfied. Okay, and what the partial fractions expansion says is you factorize the denominator is going to be 2 over from the denominator, I'm just going to factor out x, and I'll get x plus 2 dx. And we know the partial fraction going to be now 2 over x times x plus 2. You guys can see the denominator is in fact the product of two linear factors. And as a 2 for two linear factors, the term is going to be a over x plus b over x plus 2, because none of these factors, none of them is repeated. So that's why we'll get two terms in the partial fraction expansion. So next step, we have to find a and b. And when we get them, we're gonna substitute, in this integral and get it in terms of t. And we know how to find the coefficients, exactly what we're gonna do here. Here is my partial, fraction expansion. I'm gonna find now a and b. And to do so, we have to calculate the common denominator. Is gonna be a times x plus 2. So we close the brackets, plus now bx over, so the product of the two denominators is going to be just x plus 2. Right? And now we have to rearrange the numerator. And doing so, we'll get a plus b times x, a plus b, and we factor out x plus 2a over the product of the two denominators. So we'll get here x times x plus 2. So now this equality is valid if and only if the two numerators are the same, because we, as you can see, the two denominators are equal. And to get this equality, the numerator here on the left should be equal to the numerator on the right. And to do so, you guys can see the coefficient of x from the right is a plus b, and from the left, there is no x. It means, its coefficient is 0. So that's why we can say here, to get this equality valid, a plus b should be equal to 0. Because the coefficient of x here is a plus b, and from the left, the coefficient of x is 0 because there is no x. And the constant 2a here should be equal to 2. And you guys can see when you substitute, a plus b by 0 and the 2a by 2, you will get exactly the numerator equal to 2. And from this equation here, it means a equal to 1. And knowing the value of a, you substitute in the first. So it means b equal to negative a. So mean b equal to minus 1. Is it okay up to here? Any question? All right, next we're gonna substitute a and b by their values here in this equation. So we'll get now integral from 1 to t of 2 over x times x plus 2 dx. Now this integral is equal to, by using the partial fraction expansion, is going to be integral from 1 to t. And I'm going to substitute here this function. Here's the integrand by its expansion. You guys have it here. And I'm going to substitute a and b by their values. Okay, I'm just going to change the color. I'm going to replace here my function with the partial fraction expansion, where a is equal to -1 and b equal to, also a equal to 1, b equal to -1. And doing so, I'll get here. Substitute a by 1 is going to be 1 over x. And b is equal to -1. So I'll get here minus 1 over x plus 2. Dx. And now the antiderivative is quite easy. I'm gonna, because I don't have any space, I'm gonna write here the equal sign in order to get enough room. It's gonna be here ln of absolute value of x for the first function, the first term when you integrate it, minus ln of absolute value of x plus 2. Okay, and we take it like you as the FTC says at and at t. So now, so we have to calculate the integral in terms of t. So when we get it, so we're gonna go to the first line here and substitute the integral by its value and calculate the limit. Okay. Now, if you calculate this integral at t, you guys will get absolute value of t minus ln of absolute value at t plus 2. So this first bracket is obtained when you substitute x by t minus, we apply exactly what the FTC says. You substitute now by 1 is going to be ln of 1, which is 0, minus ln of 3. So there is no need to write the absolute value because it's already positive. X by 1 and going to be here 3. Okay, and this is equal to ln of absolute value of t over, I just use the property of the log function, is going to absolute value of t plus 2 minus, so we here this is equal to 0, ln of 1 going to be 0, and then you guys have minus ln of 3 going to be plus ln of 3. So get here plus because of the 2 negative sign. I just use the property of the log function. The reason is when I just leave it like that, I'll not be able to limit, because when you let t going to infinity, so we will get here infinity minus infinity, which is in determinate form. That's why I just use the property of the log function and write it as ln of t over t plus 2, because you guys know x over y is exactly equal to ln of x minus ln of y. I just use this property here. And now I'm ready to calculate the limits. I just substitute here. Now integral from 1 to infinity. of 2 over x squared plus 2x dx. So now is this equal to, just go back to, we return to the first line, and we're gonna substitute here this integral by its value that we already calculated here. The integral is right here in terms of t. Now we have to substitute in, in the first line. Is gonna be, in this case, the limit when t goes to infinity but when t goes to infinity, you guys can see this is just infinity over infinity indeterminate form. I'm just gonna write it as ln of absolute value. I just use one absolute value because the ratio of the absolute value is equal to the absolute value of the ratio. It's gonna be just t over t plus 2 plus ln of 3. Okay, now as I told you, have infinity over infinity. I can simplify. Is gonna be the limit. Okay, t is going to infinity. I don't have enough room for that. T is going to infinity, and we have t, and from the denominator I'm going to pull out t. Okay, so when I factor out t, I'll get here 1 plus 2 by t. The reason is I have infinity over infinity. That's why I just factor out in order to simplify the common factor, which is equal to t. Now I'm going to simplify here t and this t. And you guys can see here, when t goes to infinity, the numerator here is 1. The denominator is going to 1 because 2 by t is going to 0 when t goes to infinity. So it means, this absolute value is in fact approaching to 1. And the log of 1 is equal to 0. And the remaining part going to be just ln of 3. Oops. I need that. And done. Any question? Yeah. On the left here, or this line? This one? Yeah, I just substituted here. You see the a by 1 because this is exactly what I got here. You're welcome. Just wanna change the color. Oops. What I did here. So we got here a equal to 1 and b equal to -1. And I substitute here in the partial fraction decomposition. This is going to be just 1 over x. And here we'll get just -1 over x plus 2 inside the integral. Sounds good? Any question? Thank you. Are you done with the solution? Can I erase it? Okay, I'm gonna give you another one similar to this one, and you guys can, I'm gonna let you do it. Are you done, guys? I'm gonna erase it. Okay. I'm just gonna give you, the B version, and you guys can, oops, not this one. All right. And you guys have to use the same exact thing, to get this integral. I'm gonna give you 5 minutes to do it. Are you done? So you guys have to use the same approach. Okay, so partial fractions expansion. So you find the coefficients, calculate the integral, and then you calculate the limit when t goes to infinity. So you guys are done? All right, so let's see the solution. Okay, as I told you, so we first, remove infinity, subtract by t, so, and then we're going to calculate this integral. Okay, so when you factorize the denominator, as you can see, it's going to be x times x minus 1. And since we have two linear factors, we can write as a over x and b over x minus 1. So next step, we have to find the coefficients a and b. Exactly what we did in the previous example. So we calculate the common denominator. So rearrange the numerator. So a plus b should be equal to 0 and negative a equal to 3. So it means a equal to negative 3. And we substitute, the value of a in this equation, b equal to minus a. So it means b equal to 3. So next, we're going to substitute here a and b by their values and plug it inside the integral. Is it okay for the first part of the solution? Any question?
No.
Everybody got the coefficients a and b? Okay, I'm gonna let you write down, the solution, and on the next page, so we'll see how to calculate it as the integral. I'm gonna give you 1 minute to write down the solution, the first part of the solution. So you guys are done?
Yes, sir.
All right. So next page, we're gonna substitute here A and B by their values, and we substitute this function inside this integral in order to be able to calculate it. So we substitute here A by its value is equal to -3, and B is equal to 3. And we integrate term by term. So by taking 3 out, because it's a coefficient, it's going to be 3 times. You integrate -1 over x is going to be negative ln of absolute value of x. And when you integrate 1 by x minus 1, is going to be ln of x, absolute value of x minus 1. And by the FTC, we have to calculate at 2 and at t. So when you calculate it at t, you guys will get the first bracket here. So minus, you calculate it at 2. When you substitute here x by 2, it's going to be ln of 2, and here's going to be ln of 2 minus 1, going to be ln of 1, which is equal to 0. And we use exactly what we did in the previous case to get the limit. And we'll get 3 ln of 2. Example. Any question? Is there any question?
No, sir.
Thank you. All good? All right, so next I'm going to give you a second question where you guys have to use what we learned yesterday, the comparison test. Are you done with the solution? Before I move to the next question. All right, so let's now see the second question. All right, for this question, we have to use the comparison test in order to find whether or not this integral is convergent or divergent. I'm going to give you 5 minutes, and you guys have to follow what we did yesterday. And as I told you yesterday, for your quiz next week, it covers the partial fractions decomposition, the improper integral, and the comparison test. So you guys are done? All right, so let's see how to solve it. So in this case, you don't have to calculate like the previous question. You have to use the comparison test and prove whether or not this integral is convergent or divergent. Okay. Since my integral here is from 3 to infinity, so it means x is taking the values between 3 and positive infinity. So it means x is greater than 3. So that's why I'm going to start by saying, for x greater or equal to 3, because x is taking all values from 3 to positive infinity. That's why I wrote this coming from this integral. So in this case, we know cosine square of x, okay, gonna be between 1 and 0. Okay, the reason is you guys know cosine of x is always between -1 and 1. But when you square it, it becomes greater than 0 and less than 1, because the square cannot be negative. And since cosine is less than 1, the square is going to be also less than 1. Now, I'm going to multiply this by -1 because of this minus sign. I'm trying to squeeze my numerator. Okay, if you multiply by -1, so you will get -1 less or equal to minus cosine square of x, which is less than 0, right? Because you guys know cosine is positive, you will multiply by -1, it becomes less than 0. Because it's a square, it's a positive. When you multiply by -1, it becomes a negative. And now to get my numerator here, I'm going to add 2. So I'll get now 2 minus 1 less than 2 minus cosine square of x less than 0 plus 2 going to be 2. So from this double inequality, what I did is just adding 2 to this equation. If you add 2 from the right, it's going to be -1 plus 2. And here going to be minus cosine square plus 2. And here going to be 0 plus 2. And now we will get 1 less or equal to 2 minus cosine square of x less or equal to 2. And you guys can see I squeeze my numerator between 1 and 2. Now I'm going to add the denominator, and to add it, I have just to divide by the denominator. So I'll get here 1 over cubic root of x squared minus 2 is less than 2 minus cosine square of x, and you divide by the same denominator. So to get the last step here, what I did is just, from this step, I divide the double inequality by this denominator here. As I told you, I'm trying to squeeze my function in order to be able to conclude about the improper integral. So I divide cubic root of x, we square it, minus 2, and it's less than 2 over cubic root of, you just divide by the same denominator. And you guys can see I squeeze my function. But from here, you cannot conclude, because as I told you yesterday, when you guys want to use the comparison test, you have to compare your integral with one of the integrals similar to, the p integral. The integral in the is integral of type 1 because of infinity. So that's why I have to compare my integral with the integral coming from the first p test, because I have type 1 improper integral. And for the first p test, so we have integral from positive number a to infinity of 1 over x to the power p. I'm trying to compare this integral with something like that. But from this inequality, I don't have it, because the denominator is not x to the power p, is the cubic root. So that's why I have to refine my denominator in order to get something similar to 1 over x to the power p. Okay? Now how to get it? So we can say here, in addition here, on the top of what we did here, when x is greater than 3, we know squared minus 3, just gonna add here. So we have x squared minus 3, minus 2, sorry. So this is less than x squared, no matter what is x. Okay, but this is positive. Why? Because of this, our x is greater than 3. So it means the smallest value for x is 3. So 3 squared going to be 9 minus 2 going to be positive. Right? And this is my denominator. I'm going to take, the cubic root. So it means 0 is less than I'm trying to squeeze the denominator here. That's why I take this minus 2. Gonna be less than cubic root of x squared. And when I take the inverse, it's gonna be 1 over cubic root of x, because x satisfies this. X is greater than 3. That's why the cubic root gonna be greater than 0, and it's gonna be less than over and you guys can see so you guys can see this part here on the right is exactly equal to this. So what we can do from there is when we combine these two, okay, so from here and from this part, okay, so we have this. So we have 0 less than 1 over cubic root of x u squared. So since this function is less than this one, and this one from this equation is less than our function, so we can say this is less than 2 minus cubic root of x squared minus 2. Okay, you guys can see what I did is this function 1 over cubic root of x squared is less than this function, and this function here on the right is exactly equal to this one, which is less than this. And by transitivity, so it means this function is less than the function inside my integral. And this means 0 is less than this. I can write as 1 over x to the power 2 by, as I told you, I'm trying to get something similar to 1 over x to the power p, and I got it now. and it's less than 2 minus cosine square of x over cubic root of x squared minus 2. And now by the p-test, the integral of this function is divergent because p is equal to 2 by 3, which is less than 1, by the first p-test. And if the integral of this function is convergent, by the comparison test that we've seen here, it means the integral of this function is also divergent. And you're done. Just want to write our conclusion here. So according to the p-test, okay, according to the p-test, integral from 1 to positive infinity of 1 over x to the power 2 by 3. So this is divergent because p equal to 2 by 3. And saying, the integral of this function is divergent, it means the value of this integral is equal to positive infinity. If the value of this integral is positive infinity, the value of this integral cannot be equal to a number because there is no number greater than infinity. That's why this should be equal to infinity too. Now by the comparison test, that we've seen yesterday, so integral from 1 to positive infinity of 2 minus cos square of x over the cubic root of x squared minus 2 dx. So this integral is convergent. It means our integral is convergent because we found a smaller function which is convergent. And as I said, if the smaller function is convergent, it means the integral of this smaller function is equal to infinity, positive infinity, because the function is also already greater than 0. But if the integral of this function is equal to infinity, the integral of this function, which is greater than infinity, cannot be a number. Okay, it could be only infinity. And if it's equal to infinity, it means it's divergent. I see it's convergent here, divergent. The integral is divergent because this one is divergent. Any question? So the beginning, where here, here, yeah, because at the beginning I said, my x is greater than 3. It means most value for x is 3 because x is taking all values from 3 to positive infinity. So if the smallest value for x is 3, if you subtract this x by 3, you square it, it becomes minus 2 is going to be positive. That's why I said, the x squared minus 2 is positive if your x is greater than 3. Okay? And for the second inequality here, if you guys take x squared, you subtract 2, it's going to be less than x squared. If you take any number, any positive number, you subtract 2, you get a number which is smaller than your initial value. Is it okay, Mangamed? Okay. You're welcome. So x squared, you subtract 2, is going to be less than x squared. This is obvious, but the second part here is not always true, because if x equal to 1, you will get negative. But it's going to work if x is greater than 3. When x equal to 3, this is positive, and x equal to 4, same, and so on. So from 3, the first inequality is satisfied. The second inequality is satisfied for all x. Any question? All right. Now I'm going to give another one. I'm going to give you now 5 minutes to solve that. Can I erase this? All right. So let me know if you guys are still, writing the solution. Otherwise, I'm going to erase it. All right. So A, okay, I'm going to let you do this one by using the comparison test. All right. And you guys have 5 minutes to do it. So you guys are done? So what did you get, Mangabet? Convergent or divergent?
Sir, is
Yeah.
it convergent?
Fatima?
Yeah.
Yeah, it is. Thank you. Is it what you got? Convergent?
Yes.
All right. Good. Anybody else got convergent? All right, so let's solve it. We did something similar, yesterday. All right, so you try to squeeze your function, and then after that, we will be able to see if it is convergent or divergent. So for x greater than 1, because I'm integrating from 1, so it means x is in the interval 1 positive infinity. So we know sine of x is between -1 and 1, but when you it becomes between 0 and 1, and this is valid no matter what is x. It's not just because x is greater than 1, but this is valid no matter what is x. So when you square sine, it becomes greater than 0, and it's going to be also less than 1 because sine x is between -1 and 1. When you square it, it becomes between 0 and 1. Now I'm going to multiply with root of x. I'm just trying here to squeeze my numerator first, as I did in the previous example. So when I multiply, by root of x, I still have 0 less than root x sine square x. And I multiply again here by root x. So in fact, what I did is I multiply this double inequality by root x. So since the root x is positive, this will not change, the double inequalities. Okay, now I'm going to divide by the denominator here, x cubed by plus 2, the double inequality again. So what if I divide here this 0 by x cubed plus 2 still equal to 0, going to be less or equal to root x sine square x. I divide by, as I told you, so you just want to try to our function plus 2, and now we squeeze it. It's between 0 and root x over x cubed plus 2. But I'm trying, since my function is here, my integral is an integral, improper integral of type 1. I'm trying to use, the first p-test. And for the first p-test, I need to get 1 over x to the power p. And I don't have it. And now what I have to do is to refine my the right hand here is the function on the right hand side. Okay. So on the top of what we already proved, we know here x cubed, because of this x cubed is greater than 0, because we assume here x cubed is greater than 1, so that's why x cubed going to be greater than 0, and this is less than x cubed plus 2. I'm trying to squeeze the right hand side here because I don't have 1 over x to the power p. Right? If you guess x cubed plus 2 going to be greater than x cubed because you just add 2 to x cubed. It becomes, greater. Take the inverse because this is the bottom. I'm going to get here 1 over x cubed plus 2 going to be less than 1 over x cubed. And I multiply, you guys can see, I'm just going to multiply by root x. If I multiply by root x, I'll get root x less than root x of x cubed plus 2. So in fact here, to get this line, the one I'm writing, I have just to multiply, the second last is going to be 0 here. You multiply this function in the middle by root x, you will get this function, which is less than root x over x. And you guys see this function in the middle is just this function on the right. Okay.
Sir, I have a question.
Yeah.
Why did you choose the x cube?
Where? Because this is just coming from this line?
Yeah.
Yeah, because of this, the denominator. I'm trying to squeeze this function because, as I told you, since I have an improper integral of type 1, I want to use the first p-test. And for the first p-test, I supposed to get 1 over x to the power p. And from this, the first result here, I don't have 1 over x to the power p. That's why I'm trying to squeeze this function again. Okay, and to do so, I have the denominator which is equal to x cubed. I'm trying to squeeze the denominator first. That's why I just choose here x cubed plus 2 coming from this denominator. Okay.
All right.
Now, from these two double inequalities, what you guys can see is 0 is less than root x sine square x over x cubed plus 2. But this function from here is less than this function here, root x over x cubed plus 2. But root x over x plus 2, as you can see from this second double, is less than this. So we can say this is less than, by transitivity, going to be root x right? And if you calculate this right hand side, is going to be 1 over x cubed times x to the power half minus half. Because what I did here is just the last step. I just bring down this numerator, root x. And as you know, root x equal to x to the power half. When you bring it down, it becomes x to the power negative half. And when you calculate it, so you will get 1 over x to the power 5 by 2. And now I have what I was looking for. As I told you, I'm trying to get something like 1 over x to the power p. And I got it now when p equal to 5 by 2. And now by the p-test, this function, the integral of this function is convergent because p equal to 5 over 2 greater than 1. And if the integral of this function is convergent, it means the integral of this function going to be convergent, as Fatima said. So we can conclude now. So by the p-test, the integral from 1, sorry, so from 1 to positive infinity of 1 over x to the power 5 by 2 is convergent because p equal to 5 by 2 and greater than 1. That's exactly what the first p-test says. I just use the first p-test. Now, if this integral converges, so it means our integral also converges because my integrand is less than this function, which is already convergent. So we can conclude by the comparison test. Okay, by the comparison test. So the integral from 1. Irado Kunda, your mic, please. Root x sine square of x over x cubed plus 2 dx. So this integral equality here, it's less than a function which is already convergent. Any question? Is there any question?
Yeah.
Tanjis, you have a question?
Yeah, like how did you choose like the last equation when the 0 is less than like
Here,
x squared sine? Yeah.
it's just obtained from here. You can see this function is greater than 0. That's what I copy here. I just
What
copy
about
this.
like the
I just
next
copy
one?
this part here. Okay.
All right.
And since this function is less than this, the right hand side, and the right hand side is what you guys have here. It's less than this part.
Oh, yeah.
So that I combine these two double inequalities. Okay.
All right. Yeah.
Any other question? All good? Are you done with the solution?
Yes, sir.
All right, can I erase it? Okay. All right, so that's all for today. I'm gonna take the attendance before letting you go. And as I told you, so next week we're gonna do, more question, more example about it, because it's gonna be also part of your last quiz. Okay. So try to solve, the improper integrals, and also double check how to get the partial fractions decomposition.
Sir, you please let my friend into the Zoom because
Pardon?
you please let my friend join into the class because internet is
Oh,
unstable.
I cannot see him. Where is he? Nobody is in the
Uh,
waiting room.
I'm here, sir. I'm here.
Oh, okay.
Yeah, yeah. You just let me in.
Oh, okay. All right, so Magabet is here, Fatima is here. Alamin, are you here? Alamin? No? Chanky Bao?
I'm here.
Thank you. Kong Ho Dao?
Yes, sir.
Thank you. Abdullah Al Mamun?
Yes, sir, I'm here.
Thank you. Zikian Fang?
Yes, sir.
Thank you. Ali Abdullah Fardin?
Yes, sir.
Thank you. Shams Al Fardin? Shams? Not here. Mustafa Faisal?
Yes, sir.
Thank you. Fernando? Fernando, are you here? No? Pisha? Pisha Sinal?
Yep, I'm here.
Thank you. Omam Hassan?
Yes, sir.
Thank you. Trizu Cedric? Pirarukunda?
Yes, sir.
Thank you. Samar Kapil?
I'm here.
Thank you. Abdul Mushan? Not here. Ian Wan Kim?
Present.
Thank you. Kao Min Tai?
I'm here, sir.
Thank you. Inshuo Liu? Inshuo Liu?